Okay, so we're going to relate the heat energy in a substance to its temperature. And to do that, we're going to use specific heat. And specific heat is an intensive property of matter, just like density was. So, however large a piece of aluminum or iron or carbon or polyethylene is, whatever substance you want to throw out there, a glass of water, specific heat is measured in a way where it is constant for each material. Now, it can be a little bit tricky. It can change at certain temperatures, and it does change for different phases of materials. So, like, ice has a different specific heat than liquid water, which has a different specific heat than water vapor. And for the most part, it's pretty constant between the phases. Within the phase. So, like liquid water, it'll shift a little bit at different temperatures, potentially, but not much. So we usually just stick to one value throughout. Same with the ice, same with the gas. So, specific heat lets us relate the heat energy, typically in joules, to temperature of a compound in degrees Celsius. Kelvin is for gases. We're not really messing with gases here, so we'll use degrees Celsius because typically when we have a thermometer, put it in something, it's going to read in Celsius. You don't usually have Kelvin thermometers laying around. And a lot of you are going to say, well, all my thermometers are in Fahrenheit. Well, that's because they're broken. They're not real thermometers, okay? They're those weird things. They basically give everything an F. You're like, boom, how hot is my turkey? Oh, it's 210 failures, okay? That's what the thermometer is telling you. 220 degrees of failure. All right. Now it's all a social convention, whatever. I don't set my oven in degrees Celsius, okay? I don't look at the weather temperature and have any idea what, is like 27 degrees Celsius a hot day. I don't know. I live in this country. So, specific heat is the energy, so it's a constant for a material, and it's the energy required to heat 1 gram up by 1 degree Celsius. Okay? And so that means it's going to have units of joules per gram degree Celsius. Huh? How's that for fun? So it'll be some number, and that number is going to change depending on what the material is. So there's a nice table in your textbook. Table 9 point blah blah blah. I didn't write the number down. It's not a totally comprehensive list, but it has some of the nice common ones. In general, I'll give you the values when you need them. I might have missed on a practice sheet on a problem, but not this section. It'll be a later one. But if you do need that, just look at your textbook. And remember, every phase is different. So, specific heat depends on the material. So, for example, home insulation actually has a really high specific heat. It takes a lot of energy to heat up insulation, and so that allows it to be a thermal barrier between hot and cold areas. So it can be at whatever temperature it is outside your home and a more comfortable temperature inside. If it's too cold outside, insulation helps you keep your house warm. If it's the opposite, it's too hot outside, insulation will help your house stay cold by not letting the heat come through the wall. And if you want to know the effect of insulation, go in a home that's air conditioned and then walk into the garage. Oh boy, will you see the effect. So, and if you don't have any of those things, well, I think everyone here has to have AC. It's like how you have to have heat in the Midwest. But if you don't have a garage or whatever, ask a friend. Like, hey, can I go in your garage? And they'll go, why? It's 1,000,000 degrees in there. It could be 70 degrees outside, and I could almost bake cookies in my garage because it faces south. So, no, I'm kidding. It has an insulated door. So I could only get, like, food poisoning from putting cookies out there, but not actually bake them. Keeps it right in that danger zone. Alright, so things like home insulation. Well, that's going to take lots of energy. To heat it up. Because remember, energy only transfers according to temperature. So if your insulation is difficult to heat up, it's going to be a barrier to moving energy because the temperature isn't going up very quickly. Whereas something like a metal typically has a low specific heat, and so they heat up easily, they transfer heat well. So if you say you have, I don't know, aluminum windows, apparently that's the theme of this week, the glass is held in by pieces of aluminum. That aluminum will actually transfer heat very nicely around the perimeter of that window because it will heat up easily, and then it will radiate that heat into the room. It'll transfer the heat through it. The colder room will spontaneously have the heat pulled off of the aluminum. The outside will keep replacing it, and so it's kind of like a little conduit. It's like a little transfer. Whereas your walls, boom, the outside has to put a bunch of energy, so the insulation only heats up a little bit, and then only a little bit of energy leaks out into the house. The more insulation you have, thicker walls, different types, maybe you have like blow-in insulation, the more effective it is at preventing that energy transfer into your home. As well as sealing up gaps. Like if hot air can just blow in, you get that convective action, forget about insulation. Alright, so something like aluminum metal. This was literally in my notes. Not so much to complain about the windows, but it was in there because it was on my mind. This doesn't take much energy. Now you're going to think, this isn't very specific. Joe, you're writing down general heats. There's no numbers. What's going on? Well, alright. We can get a little more specific here. So aluminum, well, that's going to be 0.897 joules per gram degrees Celsius. This is also known, so specific heat is also known as C, and this would be CAL solid, because it could depend. If you actually had melted aluminum, it's actually going to have a different number here. It's going to be different. And that should be a lowercase c. I just got really excited and drew it big, just so you know. At the end of the day, it doesn't matter too much. Alright, and so then we can start understanding what temperature something is as heat is added to it. And so knowing this, we could take a question like, if we had 1.00 kilojoules of heat, that were added to, say, a 200.0 gram piece of aluminum, aluminum metal, like say, I don't know, a window frame. How much does its temperature increase? Alright, well there's a nice little equation we can use here. And so what it boils down to is if you look, you've got energy, you've got mass, and you've got temperature. And so the amount of heat in joules is going to be equal to this constant times however many grams there are of the substance times whatever change in temperature it has. So, Q is the heat. This isn't my thing. It's the actual general variable for it. Okay? Because you can't spell heat without Q. All the good letters were taken. You'll see H was taken. E is taken for energy. A is actually a constant for something. T, lowercase t is time. Capital T is temperature. All the letters are taken, so we went with, I don't know, we're like, what's left? Q. Alright? Okay, cool. Q. Hopefully we don't actually have anything that starts with a Q later. It turns out we do, but it's cool because we use capital Q for that, and that's a ways down the road. Alright, so it's equal to MC delta T. Q equals MCAT. So M is mass, C is our specific heat, and delta T is our change in temperature. So this allows us to figure out the change. So if we know where we start, we know the change, boom, we can add them together, we get the final temperature. And so for this problem, move it over here so I have room to write. We need to find delta T, because we want to know how much does the temperature increase. Well, that's delta T. And so that's going to equal Q over MC. We know all these variables. That's our Q. We'll have to convert it to joules because our constant is going to have units of joules, because there's our C and there's our M. So we've got all our pieces. Let's put it together. So I'm going to have 1.00 kilojoules. Alright. But that means I have 1,000 joules per kilojoule. Getting tight over here, but I made it work. Alright. Our mass is 200 grams. And our constant, I'm going to have to sneak that down here, but it is in the denominator, is this guy right here. It has some wonky units, so I need more room to write it. 897 joules per gram degree C. Alright, we punch it up in our calculator, so it ends up being 1,000 divided by 200 times that number. And we get plus 5.7 degrees Celsius. So we're going to go up about 5.5 degrees Celsius. Alright, now we can add an extra detail here. What if we know the initial temperature? Then we can know what temperature we land at. You know, maybe it was 0 degrees, then okay, we end at 5.57. Maybe it was 100 degrees, then we end at 105.57 degrees Celsius. But, you know, odds are it's something more like room temperature. So, it was originally at, we'll say 25.00 degrees Celsius. What are the odds of that? It's like the numbers a student would make up in lab or something. What is the final temperature? Alright, well, keep in mind, delta T is our final temperature minus our initial. And so if we know our initial, and we know our final, or our change, excuse me, then we can solve for our final. So it's delta T plus Ti, initial temperature. And so in this case, our delta T we solved for, it was 5.57 degrees Celsius. Our initial is 25.00 degrees Celsius. We solve that bad boy, we get 30.57 degrees Celsius. Is that hot? I don't know. It's warm at least, I think. Ask a Canadian, or a European, or an Australian, or a South American, or someone from Africa, or, you know, basically anywhere but here. I think, I want to say, maybe Jamaica still uses Fahrenheit. I think they still use the mile. There's this issue though, there was like our mile, and there was a British mile that was actually different. So it's a bit of a mess. There's imperial miles, American miles. Everyone uses the same kilometer though, I'll say that. For example, our kilometer is, well, we don't have one. We don't use it. But if we did, it'd be the same. So here's kind of the takeaway. Alright, so I showed you what to do with the math, but here's kind of the general stuff to keep in mind. And this is gonna be mind-boggling, by the way. Alright, you probably never knew this before. But if you add heat to something, it's gonna get hotter, temperature is gonna go up. Well, guess what? You can also remove heat from stuff. And guess what happens? You're going to lower the temperature. Now, the new idea is you might have thought temperature and heat were exactly the same thing. And they're not. You have to convert between them using a specific heat. Now, how much? This is a general term. You know. But how much temperature changes? You know, if we're going to talk about this more exactly, well, it's going to depend on two things. One, what it is, aluminum is going to heat up differently than iron, is going to heat up differently than gold, is going to heat up differently than water, and so on. It's going to heat up differently than helium gas, so on and so forth. So what the material is, and 2, how much of it there is. You know, if an object is twice as large, it's going to heat up twice as slowly. Right? Remember, there's Q equals mc delta T. Well, the relationship between heat and temperature depends on what the substance is. It's going to decide C, and how much there is, the mass as well. So it's going to depend on how much, how many grams of material there is. It's also known as thermal mass. You might have heard that term before. So that gives us a nice, strong base for relating temperature to heat. So, temperature is things like degrees Celsius, Kelvin, degrees Fahrenheit. Heat is stuff like joules and calories. They're different ideas. They're connected, but they're different ideas. So you have to be careful there. Alright, so next we're going to talk about energy and chemical equations. So we're going to bring chemical equations back into the fold. So we've talked about kind of the basic stuff of heat and energy and temperature. We've built that foundation. Now we're going to pull the chemistry back into this. We're going to see balanced chemical equations with a new little detail on them. Alright, so that's what we're doing next. And we'll just keep working through here.